Regex can feel unreadable. But most interview-style regex tasks follow a few simple patterns. In this video, we will solve 16 practical Python regex problems with clear input, output, and explanations so you can finally understand how pattern matching works. We start with the core regex skills juniors use all the time: finding patterns and validating full strings. These examples are small, but they show habits that matter in real code. Real text often mixes words and numbers, and we usually need only the numeric parts. Let's write a tiny script that scans an order message, finds every group of digits, and then we run it to see the exact list Python gives us. Let's break down why this works. The pattern uses D for a digit, and plus means keep matching digits while they continue. Because we used findAll, Python collects all matching chunks instead of stopping after the first one. Now let's show the safer habit. For regex patterns in Python, use raw strings because they keep backslashes clear and predictable. This becomes much more important when patterns grow beyond 1 or 2 symbols. For practice, change the message so the price is 59.99. Then adjust the regex so the decimal price is captured as one value, not 2 separate numbers. Signup forms often need a simple username rule. Only letters, digits, and underscores with a reasonable length. Let's test 4 usernames against one pattern, then run the script and inspect which values pass. Let's break down the rule. The character class allows uppercase letters, lowercase letters, digits, and underscore. The length quantifier requires 3 to 16 characters, so bad name fails because of the dash, and ab fails because it is too short. Now let's show the validation habit I prefer. When the whole string must match, refull match says that directly in the code. It reduces the chance that someone later changes the pattern and accidentally validates only part of the input. For practice, add 3 more usernames and predict the result first. Test admin, a username longer than 16 characters and a username with a space inside it. Now we move from tiny patterns to useful extraction tasks. Emails and dates appear constantly in logs, tickets, forms, and imported data. Support notes and CRM exports often contain email addresses mixed into normal text. Let's write a practical pattern. Search the whole sentence and now run the script to see the 2 addresses returned as a list. Let's break down the shape instead of memorizing it. Before the @ sign, we allow common email characters. After it, we allow domain characters. Then we escape the dot because a plain dot in regex means any character. Now let's show the practical boundary. This pattern is good for finding email-like text in real content, but strict email validation has many special cases. For production validation, use a dedicated library or your framework's validator. For practice, add 1 more address to the text and run the same pattern again. Try supportdevlevel.io and check that the result now contains 3 matches. Dates often appear inside bigger strings, like invoice lines or log messages. Let's search for a YYY's AMMDD date, capture each part, and now run the script to print the year, month, and day separately. Let's break down the groups. The first group captures 4 digits for the year, then 2 digits for the month, and 2 digits for the day. When we call groups, Python gives us those captured pieces as separate strings. Now let's show the important production rule. Regex can find something that looks like a date, but it does not prove the date is real. After extraction, pass the value to datetime when correctness matters. For practice, change the input line to another date and keep the same pattern. Try 2025-12-31, then confirm the output updates without changing the extraction logic. The last task in this batch is about cleanup. Regex is not only for extracting data, it is also very useful for normalizing messy text. Scraped or copied text often has extra spaces, line breaks, and tabs mixed together. Let's replace every run of whitespace with 1 space, then run the script and check the clean sentence. Let's break down the cleanup. The whitespace class matches spaces, new lines, and tabs because we use plus. Several whitespace characters in a row become 1 match, and retub turns that whole match into a single space. Now let's show the final polish. After replacing whitespace, call strip when leading or trailing spaces might exist. That keeps the clean value ready for storage, display, or test comparisons. For practice, add extra spaces at the beginning and end of the input. Then remove strip for 1 run and compare the output, so you can see exactly why that final cleanup step matters. In this section, we use regex to clean sensitive text before it leaves our application. When logs are shared with a team, Personal phone numbers should not stay visible. Let's write a regex that recognizes two common formats, one with dashes and one with dots, then run the script and check the redacted text. Let's break down why the output has two placeholders. The non-capturing group gives the regex two alternatives, and each alternative matches one full phone number format. Because resub replaces all matches by default, both numbers disappear from the final text. Now let's show the safer habit for real projects. Test redaction patterns with real examples. Missing private data is usually more dangerous than hiding a little too much, so keep examples for every format you expect to remove. For practice, adjust the pattern so it also handles spaces between number groups. The target variation is 555 space 123 space 457, and it should also become. Now we use regex to parse compact text formats that are common in user input and configuration strings. In real forms, users mix commas, semicolons, and random spaces when they type tags. Let's use resplit with a separator character class, then run it and see if we get clean tag names. Let's break down the separator. The square brackets mean any one of these separator characters, and the plus means one or more in a row. That is why two spaces between interview and junior behave like one separator. Now let's show the practical guard you usually want around this pattern. If input can start or end with separators, filter empty strings after splitting so the list only contains real tags. For practice, make the parser accept pipe characters too. The input should handle Python pipe regex while still supporting commas, semicolons, and spaces. Configuration text is often compact, but the program wants structured data. Let's scan every key equals value pair with named groups, build a dictionary, and run the code to verify the parsed settings. Let's unpack the result. Each match has two named parts, key before the equals sign and value after it. Because we loop over all matches, the dictionary gets one entry for host, one for port, and one for debug. Now let's show the maintainable version to remember. When a regex has multiple captured parts, named groups make the parsing code easier to read and safer to change later. For practice, reuse the same idea with another config string, parse user, retries, and mode into a dictionary, then print the result. In validation tasks, regex is useful for structure, but Python should often handle the final logic. A valid IPv4 address needs 4 numbers, and each number must be from 0 to 255. Let's first use regex to check the dot-separated structure, then run Python logic for the numeric range and print each result. Let's explain the two checks. The regex rejects 10.0.0 because it does not have 4 parts. The integer check rejects 256.1.1 because 256 is outside the valid IPv4 octet range. Now let's show the important interview takeaway. Do not turn a simple numeric check into a huge unreadable regex just to look clever. Use regex for the shape and normal Python for the range. For practice, add one more rule. Reject leading zeros like 001, but still allow the single-digit 0. This is a good small extension because it keeps structure and validation clearly separated. This section focuses on finding useful context around a match, not just detecting that a match exists. Application logs are easier to scan when we can pull out the word next to an important keyword. Let's find the word immediately after error, use a case-insensitive search, and run the code to see the matches. Let's break down the capture. The regex finds error as a separate word, skips the spaces after it, and captures the next word only, because find all returns captured groups. The output is just database and cache. Now let's show the clean intent. Use reignore case when capitalization does not matter. It is clearer than writing a pattern with every uppercase and lowercase letter combination. For practice, capture 2 words after each error instead of 1. The result should become database timeout and cache miss, which is often more useful for log summaries. Now we move into text transformation. These problems are about changing real strings safely, not just finding matches. When data comes from spreadsheets or exports, dates often arrive in the wrong format. Let's write a regex that captures month, day, and year as separate parts, then uses read a sub to rearrange them. Now we run the script and look at the transformed sentence. Let's break down why this works. The first group is the month, the second group is the day, and the third group is the year. The replacement string writes group 3 first, then group 1, then group 2, so every match date becomes ISO style. Now we show the best habit for this kind of replacement. Keep each date part in its own explicit group because it makes the transformation easy to read and safer to review later. For practice, add another date like 01092027 to the same text. Your goal is to make the output include 2027-0109 without changing the replacement logic. Generated text and user comments can accidentally repeat words. Let's capture one word, look for the same word right after it, and replace both copies with just one. Now we run the script and check that the sentence is clean. Let's break down the match. The group captures a full word, then the back reference asks for that exact same text again after some white space. Because the replacement is only group 1, the duplicate disappears. Now we show the safer version of the idea. Use word boundaries around the captured word because without them, a regex can match inside larger words and create strange replacements. For practice, try cleaning the sentence go now add reignore case. So the first duplicate is removed even though the capitalization is different. This section focuses on a classic regex interview trap, greedy matching. The goal is to see the wrong result first, then fix it with a lazy pattern. Quoted values often show up in command output and simple config text. Let's first print a greedy match so we can see the problem, then print the lazy version that extracts each value separately. Now we run it and compare both lines. Let's explain the two outputs. The greedy dot star keeps expanding until the last quote in the whole string, so it returns one oversized value. The lazy dot star stops as soon as it can, which gives us alpha and fast as separate matches. Now we show the better production habit. When you know quotes are the boundary, a specific character class is clearer than dot star because it says, match anything except a quote. For practice, replace the lazy pattern with the character class version. The output should still be alpha and fast, but the pattern will be more explicit. Now we use flags to change how a pattern behaves. The important idea is that anchors can mean different things when multi-line mode is enabled. Application logs usually come as one multi-line string, but we may only care about errors. Let's use anchors to match lines that start with error and enable re-ulti lines so those anchors work per line. Now we run the script and check the extracted messages. Let's break down the flag. Without multi-line mode, the start anchor only means the start of the whole string. With multi-line, it also means the start of each line, so the regex can find both error entries. Now we show the best habit for log parsing. Use flags deliberately, and keep the pattern small enough that another developer can quickly see which lines it accepts. For practice, add another error line like disk full to the multi-line log. Run the same pattern again and confirm the new message appears in the list. The final problem in this batch uses context-aware matching. Lookarounds let us check what is around a value without including that context in the result. Sometimes we only want a number when it appears in the right context. Here the context is a $ before the amount, so we use a positive look behind and keep the match itself clean. Now we run the script and make sure the euro value is ignored. Let's unpack the result. The look behind checks that a $ is immediately before the number, but it does not become part of the return text. That is why the list contains 19 and 5.99 without $ and skips 20 euros. Now we show the practical rule for lookarounds. Use them when the context matters but should not be part of the value, and keep the pattern readable enough to debug quickly. For practice, add another amount like 100.50 to the string. The same pattern should return 19, 5.99 and 100.50 while still ignoring non-dollar numbers. In this section, we look at regex performance problems that can turn a simple validation check into a slow or unsafe operation. In real services, a slow validation regex can freeze a request handler if someone sends malicious or just unexpected input. Here we create a string that almost matches, 25 characters followed by an exclamation mark, then we time two patterns with perf counter. Now we run the script and compare the risky nested quantifier with the safer direct pattern. Let's break down why the result is so different. The risky pattern has a plus inside a repeated group, so the regex engine can partition the same run of a characters in many ways. When the final exclamation mark makes the match fail, the engine keeps trying alternatives before it finally gives up. Now let's show the safer rule to remember, because this is the version you want in user-facing validation. Avoid nested ambiguous quantifiers like a plus inside another plus, especially around groups that can match the same characters. Prefer a direct pattern or redesign the validation into simpler checks when the regex starts getting clever? For practice, change the input size and watch how the risky pattern behaves. Try 28 characters followed by an exclamation mark, then replace the risky pattern with a simpler direct pattern. The goal is to train yourself to test regexes against the cases that fail late. You now have 16 real regex examples you can reuse in interviews, projects, and daily Python work. Subscribe for more practical Python challenges, like the video if it helped, and comment with the topic you want next.